Hello student, welcome to the EPG Pathshala. I am Ashok Goel from the Department of Physics and Astrophysics. Today we are going to discuss in this module the Fredholm equations, Neumann series and the degenerate kernels from the paper Mathematical Physics Part 2. So students, let us see what we are going to learn in this module. In this module, we are going to learn the use of Neumann series in solving integral equations. We will learn about degenerate kernels and give some examples in physics and mathematics. Consider the Fredholm integral equation f of x is equal to gx plus lambda integral a to b kx x1 fx1 dx1. This equation is an equation in the unknown function f of x. It has an inhomogeneous term g of x and the kernel is kx x1 and there is a constant lambda multiplied to the kernel. Before we attempt to determine the unknown function f of x as power series in lambda, in lowest order of lambda, we have f of x equaling f0 is equal to phi 0x, where phi 0x is simply equal to the inhomogeneous term gx. When we substitute this approximant in the integral term, we obtain the next approximant f1x, which differs from fx by terms of order lambda square. So f1x is equal to phi naught x plus phi 1x, which phi naught x is g of x, phi 1x is lambda times the integral a to b kxx gx1 dx1 plus terms of order lambda square. Continuing in this way, we get the next approximation f2x in terms order lambda cube. So f2x can be written as phi 0x plus phi 1x plus phi 2x, which in turn is equal to g of x plus lambda integral a to b k xx gx1 dx1 plus lambda square term, which is lambda square multiplied to the integral a to b kx x1 dx1, and the whole thing is again multiplied by an integral from a to b of the kernel x1 x2 multiplied by the function g of x2 dx2. Now from this zeroth order term, first order term and the second order term, we can discern what will be the general term. So the form of the nth approximant, if we continue in this way, is easy to decipher, and we obtain fn of x, which is nth order term, is equal to gx plus lambda integral from a to b over x1, the integrand being kxx prime gx plus lambda square, product of two integrals, one integral over dx1, which involves only the kernel, which is a function of kxx prime, multiply the integral again from a to b over dx2 of the kernel x1 x2 multiplied by the function gx2. And we continue this. The nth term is obviously lambda to the power n and the product of integrals. The integrals in this product are, for example, a to b dx1 of kxx1 continue till the last term in the integral is an integral over dxn between the limits a to b of the product of the kernel, which is a function of k xn n minus 1 and xn multiplied by the function g, which is a function of xn. Now in the limit n goes to infinity, we write f of x is the limit of fnx as n goes to infinity, which can be written as limit n goes to infinity of a series, which can write in the form of summation the sigma I is equal to 0 to infinity lambda to the power I integral multiple integral from a to b of dx1 dx2 dxi, the integrand being the product of kernels k x and x1, another kernel which is a function of x1, x2, till kernel, which is a function of xi minus 1 and xi, and multiplied by the function g of xi. Now we have to see whether the series exists or not, the series converges or not. If the limits a and b are finite, a sufficient condition for convergence can be worked out easily. Let the variable x lie in the region a to b and another variable y lies in the region a to b. Then the kernel k, which is a function of two variables x and y, is assumed to be bounded by some number capital K, and similarly in the region x lying between a and b, let mod of g be also bounded by a number capital G. Then the nth term in this series above can be seen to have a bound, namely mod of lambda to the power n multiplied by mod of g multiplied by the mod of k raised to the power n multiplied by the mod of b minus a to the power n. Now we can use Cauchy's condition for the convergence of an infinite series. A sufficient condition for the convergence is that lambda mod into k mod into the mod of b minus a is less than 1. Because if this product lambda mod k mod b minus a mod is less than 1, then obviously the product mod lambda to the power n, mod g, mod k to the power n, mod b minus a to the power n is less than 1. This, we emphasize, is a sufficiency condition which is useful if b minus a is finite and mod lambda is small enough. To answer the question of convergence in a more general way, we need a more accurate analysis, which we will discuss shortly. Now, before we discuss more accurate analysis, with the help of certain examples, let us illustrate what we have done. So, let us consider an example of an integral equation which is inhomogeneous. The integral equation being given by f of x is equal to 1 plus lambda, integral from 0 to 1 over dy of a product of x minus y into f of y. So, see, in this equation, the inhomogeneous term g of x is simply equal to 1. The limits are from 0 to 1 and the kernel k, which is function x and y, is x minus y. So, let us see how we obtain the first three terms of the Neumann series of this equation. Obviously, in the lowest order in lambda, f0x is equal to 1. Now, f1x is equal to 1 plus lambda integral 0 to 1 x minus y, and substitute f of the lowest order term for f of y, which is f0y, which is equal to 1. So, you have f1x is equal to 1 plus lambda integral 0 to 1 x minus y 1 dy, which is equal to 1 plus lambda x by 2 minus y by 1 by 8. Next term f2x is equal to f0 plus f1x. f0x is 1, f1x is this lambda x by 2 minus 1 by 8 plus the next term is lambda square integral 0 to 1 x minus y. Substitute for fy this term, which is x by 2 minus 1 by 8 integrated over dy. So this integral can be evaluated and we get for the f2x the terms f2x is equal to 1 plus lambda x by 2 minus 1 by 8 minus lambda square by 192. This is the way we can get the successive terms in the Neumann series of the equation. So we illustrated this by getting the first three terms for this equation. We consider another example where we are asked to determine the nth term in the Neumann series of the integral equation. The integral equation in this case is f of x is equal to 5x plus 1 plus 1 half integral from minus 1 to 1 t minus x ft dt. That is, the inhomogeneous term is 1 plus 5x, lambda is 1 half, kernel is t minus x. The zeroth order term is obviously fx is equal to f naught x is equal to phi naught x, which we write equal to 5x plus 1. The first order term is f of x is equal to phi naught x plus phi 1x, where phi 1x is equal to half times the integral minus 1 to 1 t minus x where f t is replaced by phi 0 t. So phi 0 t dt, but phi 0 t is equal to 5t plus 1. So this phi 1 x is equal to 1 half from minus 1 to 1 integral over dt t minus x 5t plus 1. This integral can be done easily. We get 5 by 3 minus x. Continuing in this way, phi n x is equal to 1 half integral minus 1 to 1 over dt of t minus x multiplied by the function phi of n minus 1 t, where phi n minus 1 is the phi correct to nth order. All the phi's, remember, are linear in x. So let's write phi n x to be anx plus bn. So since all phi's are linear, so they are all of the type ax plus b. So let us write phi n x is equal to anx plus bn. Then anx plus bn is equal to half times the integral minus 1 to 1 dt of t minus x a n minus 1 t plus b n minus 1, which can be evaluated. So phi n x will look like a n minus 1 by 2 multiplied by 2 by 3 minus 0 times x plus b of n minus 1 by 2 multiplied by 0 minus 2x, which is equal to minus bn minus 1 times x plus an minus 1 by 3. So hence an is equal to minus bn minus 1 and bn is equal to an minus 2 by 3. Or alternatively, we can write an is equal to minus an minus 2 by 3. So we have a1 n minus 1 to the power n, a naught by 3 to the power n is equal to minus 1 to the power n, 5 by 3 to the power n for n is equal to 0, 1, 2, b 2n plus 1 is equal to an x by 3, which n is equal to 0, 1, 2, and so on and so forth. b2n is minus 8a 2n plus 1 is minus 1 to the power n divided by 3 to the power n. A little involved algebra. So if you do it yourself, you can see one can easily obtain these terms. Hence the function fx can be written as f of x is equal to phi naught of x plus phi 1 of x plus phi 2 of x plus phi 3 of x and so on, which can be written in the form that fx is equal to sigma n is equal to 0 to infinity of phi 2n x plus sigma for n is equal to 0 to infinity phi 2n plus 1 of x, which now substituting for the phi 2n and phi 2n plus 1 from the previous slide. So f of x can be written as summation over n from n is equal to 0 to infinity of a0 minus 1 to the power n by 3 to the power n times x minus 1 to the power n a0 divided by 3 to the power n plus sum over n is equal to 0 to infinity of a1 minus 1 to the power n by divided by 3 to the power n x plus minus 1 by 3 a0 by 3 to the n, which is equal to 5x multiplied by 1 upon 1 plus 1/3 plus 1 upon 1 plus 1/3 plus minus 1 times x divided by 1 plus 1/3 plus 5 by 3 multiplied by 1 upon 1 plus 1/3, which is nothing but 3x plus 2. So fx is equal to 3x plus 2 is a complete solution of the equation which we consider, and it's worthwhile to substitute this value f of x in the integral equation to see this is indeed the solution. Now we discuss Fredholm equations and degenerate kernels. Degenerate kernels are also called separable kernels. They are defined to be kernels kxy which can be separated as a product of two functions. In general, a function is degenerate or separable if the kernel kxy can be written as a summation of a product of two functions pi of x multiplied by hi of x for all values of I from 1 to n. Pix and Pi of x and Hi of y can be any continuous functions of the arguments. Quite often, the kernel k, which is a function of x and y, is generally a function of only the difference between x and y and can be expressed in the form shown above. Thus, if the kernel k depends only on x and y through this combination x minus y, that is, if the kernel kx minus y, for example, is equal to exponential x minus y, the kernel is degenerate. Kernel kx minus y is sine of x minus y is equal to sine of x cosine y minus cosine x of sine y is another example of a degenerate kernel. But if you look at the kernel, which is defined as kxy is the tangent of x minus y, which is of course expanding the tangent as tan a tan b minus divided by 1 plus tan a tan b. So the kernel k of x and y, x minus y, which if has the functional dependence like the tangent of x minus y, which in turn is equal to tangent x minus tangent y divided by 1 plus tangent x plus tangent y, cannot be separated and is therefore not degenerate. Fredholm equation with degenerate kernels can be written as. We now consider the case of degenerate kernel of the Fredholm equation. So continuing, we have fx is equal to gx plus lambda integral a to b kxy f of y dy equal to g of x plus a to b. The kernel k is written in terms of a product, sum of the products, sigma over I of a function pi, which is a function of x alone, multiplied by a function of y alone, which is hi, into of course the function f of y dy. Let ai is equal to integral a to b h I of y f of y dy. So we integrate out over y. Remember, see that the function pi's are functions of x only, so we can do the integration over y. So this integral over y, once it's done between the limits a and b, is obviously some number which we have written here as alpha I. Since fy at this stage is unknown, alpha i's at this stage are known numbers. The integral equation then reads f of x is equal to g of x plus lambda sigma over j from 1 to n pjx into alpha j. Now multiply the equation by hix and integrate over x from a to b. The left hand side is simply an integral from a to b of a product of two functions fx and the function hix with which we have multiplied it, and which from our definition is simply equal to alpha I. Thus we get alpha I is equal to gi plus lambda, a sum over j is equal to 1 to n hij alpha j, where gi is this integral from a to b of dx or gx and hix, and hij is an integral over dx between the limits a to b of the product of the function hi, which is a function of x, and the function pj, which is again a function of x. So hij is also a number. This equation represents a set of linear algebraic equations for the unknown alpha I. Alpha I is unknown, they are n in number. So in the matrix form, if we write alpha as a column vector, alpha 1, alpha 2, alpha n, and g another column vector with entries as g1, g2, gn, then H is a n by n matrix with the entries as hij, h11, h12, etc. And then this equation simply can be written in the matrix form as alpha is equal to g plus lambda ha, or we can write 1 minus lambda ha is 1 minus lambda h operating on this column vector alpha gives us the column vector G, where we have introduced a unit matrix I. So, where I is a n by n unit matrix. Solving this, we get alpha is equal to inverse of a matrix which is the unit matrix I minus lambda times the matrix H and multiply by the column vector G. The theory of linear algebraic equations tell us that if Gx is equal to 0, that is, the given integral equation is a homogeneous equation, then the right hand side of the equation which we have considered is 0 too. A non-trivial solution, that is alpha not equal to 0, of the eigenvalue equation I minus lambda h operating on alpha is equal to 0 that exists. Say I is a unit matrix, say n by n, H is a matrix of n by n, alpha is a column vector. So this is an eigenvalue equation. So the equation I minus lambda h operating on alpha equal to 0 exists if and only if the determinant of the matrix I minus lambda h is equal to 0. The solution to the homogeneous equation, that is for Gx equal to 0, exists for such values of lambda that satisfy the above equation. We can then write the matrix H operating on alpha or H alpha is equal to lambda inverse alpha. Now this is an eigenvalue equation. It has non-trivial eigenfunctions alpha not equal to 0, which are the solutions. They exist only for values of lambda inverse such that the determinant of the matrix I minus lambda h is equal to 0. Such values of alpha are called the eigenvectors and lambda inverse are the eigenvalues of h. Each non-trivial eigenvector alpha gives us a solution of the homogeneous equation. The number of linearly independent non-trivial solution is well known from linear algebra. Let us enumerate here the results from linear algebra. If all the eigenvalues are simple, that is, if the equation determinant of the matrix I minus lambda h is equal to 0. Now look at this is a determinant of n by n matrix, so it's a polynomial equation of degree n. For lambda has n distinct solutions, then if lambda has n distinct solutions, then one has n linearly independent eigenvectors alpha, one for each eigenvalue lambda inverse. If any eigenvalue is repeated k times, where obviously k is less than or equal to n, in the case k equal to n, all eigenvalues are the same, then we may have 1 to k eigenvectors corresponding to that eigenvalue depending on the matrix H. If the inhomogeneous term Gx is not equal to 0, then for a solution to exist, the matrix I minus lambda h must be invertible, which again means that the determinant of the matrix is not equal to 0. Thus, this allows 1 minus lambda h inverse to be evaluated. Once that is done, all the alpha i's can be calculated and then we obtain the required solution using the alpha i's thus determined. We now consider an example of an integral equation where f of x is equal to x times 4x minus 3 plus lambda times an integral from 0 to 1 of dy 2x square plus 2y minus 1 f of y. In the language of equation, the kernel kxy can be written as a sum over I is equal to 1 to n pix hiy. So this is an equation with n is equal to 2 and p1x is equal to 2x square minus 1, h1 is equal to 1, gx is equal to x. Thus, p2x is equal to 1, h2 x is equal to 2x. Hence, gi is given by the integral from a to b of dx, gx into hix. Thus, g1 is integral from 0 to 1 of dx, and now substitute for g1 and h1. So, which is 4x square minus 3x into 1, integral is minus 1 by 6. Therefore, g1 is minus 1 by 6. g2 likewise can be calculated to be 0. h11 is an integral from 0 to 1 of 2x square minus 1 dx, which is minus 1, 3. h12 is 1. h21 is integral 0 to 1 dx of the product of 2x into 2x square minus 1, which is equal to 0. h22 is 0 to 1 dx, 2x equal to 1. With the g1, g2 known, h11, h12, h21 and h22 known, we have the matrix as a 2 by 2 matrix, and the column vector has entries minus 1 by 6 and 0. So the determinant of I minus lambda h is equal to determinant of 1 plus lambda by 3, lambda, 0, 1 minus lambda, which is equal to 1 plus lambda by 3 into 1 minus lambda. Hence, the condition gives two eigenvalues, because for the solution to exist, the determinant should be equal to 0. So, determinant is equal to 0 for lambda is equal to 1 and lambda is equal to minus 3. Therefore, there are two eigenvalues. Lambda is equal to 1 and lambda is equal to minus 3. Thus, the solution of the inhomogeneous equation above can be written in the matrix form. Vector alpha 1, alpha 2 is equal to the vector multiplication of a 2 by 2 matrix with entries 1 minus lambda, 1 lambda by 3 in the diagonal elements, minus lambda and 0 in the off diagonal elements, multiplied by the column vector minus 1 by 6 lambda 0 divided by 1 plus lambda by 3 into 1 minus lambda. So this can be multiplied, and one can see that this is simply equal to minus 1 upon 6 plus 2 lambda and 0. So alpha 1, alpha 2 are the two components of a column vector, where alpha 1 is minus 1 upon 6 plus 2 lambda and alpha 2 is equal to 0. Hence, f of x is equal to 4x square minus 3x minus lambda into 2x square minus 1 divided by 6 plus 2 lambda, which is the final solution for the equation, provided lambda is not equal to 1 and also not equal to minus 3. So students, let us summarize what we have learned in this module. In this module, we have learned the use of Neumann series, and this use is elaborated for solving Fredholm equations. The special simplifying nature of degenerate kernels is highlighted and some properties mentioned. Thank you.